Stellar mass black hole mergers. When two stellar mass black holes approach each other, they begin a cosmic dance that spans millions of years before culminating in one of the universe's most violent events. Stellar mass black holes form when stars at least 8 to 10 times more massive than our Sun reach the end of their lives and collapse under their own gravity. These collapsed stellar cores typically range from 5 to 50 times the mass of our Sun, compressed into regions just 20 to 30 kilometers across. The merger process begins when two stellar mass black holes find themselves in a binary system. This can happen in several ways. Sometimes, two massive stars in a binary system both evolve and collapse into black holes, while remaining gravitationally bound. Other times, black holes can capture each other through gravitational interactions in dense stellar environments, like globular clusters or galactic centers. Initially, the two black holes orbit each other at relatively large distances, perhaps hundreds or thousands of times the distance between Earth and the Sunday. At this stage, they lose energy very slowly through the emission of gravitational waves. These ripples in spacetime carry away orbital energy, causing the black holes to spiral inward toward each other. This inspiral phase can last for billions of years, with the black holes gradually drawing closer together. As the black holes approach within a few hundred kilometers of each other, the gravitational wave emission intensifies dramatically. The objects begin orbiting each other hundreds of times per second, reaching speeds that are significant fractions of the speed of light. During these final moments, each black hole experiences extreme tidal forces from its companion. But because they have no physical surface or internal structure, they remain intact as they spiral inward. The actual merger occurs when the two event horizons touch and combine. This happens in a fraction of a second, creating a single, more massive black hole. The newly formed black hole initially has a highly distorted shape and rings like a struck bell, emitting powerful gravitational waves as it settles into a stable, spherical configuration. This ringdown phase lasts only milliseconds, but releases enormous amounts of energy in the form of gravitational waves. During the final merger, typically 1 to 5% of the total mass of the system gets converted directly into gravitational wave energy. For two 30 solar mass black holes merging, this means roughly 1 to 3 solar masses worth of energy radiates away as gravitational waves in just a few seconds. This energy output can briefly exceed the combined light emission of all stars in the observable universe. Intermediate mass black hole mergers. Intermediate mass black holes occupy a mysterious middle ground between stellar mass and supermassive black holes, with masses ranging from 100 to 100,000 times that of our Sunday. These objects present one of the greatest puzzles in modern astrophysics because we lack a clear understanding of how they form, making their mergers particularly intriguing and rare to observe. The formation pathways for intermediate mass black holes remain hotly debated. One possibility involves the direct collapse of massive gas clouds in the early universe, bypassing the normal stellar evolution process. Another scenario suggests they form through the repeated mergers of smaller stellar mass black holes in dense stellar environments. Some theories propose they originate from the collapse of the first generation of stars, known as population 3 stars, which could have been hundreds of times more massive than typical stars today. When intermediate mass black holes merge, the process follows similar physics to stellar mass mergers, but on dramatically different scales. The inspiral phase can last for hundreds of millions of years, as the objects slowly lose energy through gravitational wave emission. Because these black holes are more massive, they orbit each other more slowly during the final approach, taking minutes or hours to complete their final spirals, rather than the milliseconds characteristic of stellar mass mergers. The gravitational waves produced by intermediate mass black hole mergers have much lower frequencies than those from stellar mass systems. While stellar mass mergers produce waves in the audio frequency range that ground-based detectors like LIGO can observe, intermediate mass mergers generate waves in the millihertz range. These lower frequency waves require space-based detectors or specialized analysis techniques to detect. During the merger itself, the energy release scales with the total mass of the system. Two intermediate mass black holes, each containing 1,000 solar masses, can convert 10 to 50 solar masses worth of material into pure gravitational wave energy. This represents an enormous release of energy, though it occurs over a longer timescale than stellar mass mergers. The resulting black hole from an intermediate mass merger can approach or exceed the lower mass limit for supermassive black holes. This process may represent one pathway for growing the seed black holes that eventually become the supermassive monsters found at the centers of galaxies. The merger remnant typically has a mass between 70 and 90% of the combined original masses, with the remainder radiated away as gravitational waves. Supermassive black hole mergers. Supermassive black holes contain millions to billions of times the mass of our Sun and reside at the centers of most galaxies. When galaxies collide and merge, their central supermassive black holes eventually find each other through gravitational interactions, setting the stage for the most energetic merger events in the universe. The merger process begins when two galaxies approach each other over hundreds of millions of years. As the galaxies interact gravitationally, their shapes become distorted, forming tidal tails and bridges of stars and gas. During this galactic dance, the supermassive black holes at each galaxy's center begin their own slow approach toward each other. Initially separated by hundreds of thousands of light years, they gradually spiral inward as dynamical friction with surrounding stars and gas removes energy from their orbit. When the black holes reach separations of a few thousand light years, they enter what astronomers call the hard binary phase. At this stage, gravitational interactions with individual stars become the primary mechanism for removing orbital energy. Stars that pass close to the binary system can be ejected at high velocities, carrying away energy and allowing the black holes to continue their inward spiral. This process can stall if there are insufficient stars in the galactic center to facilitate continued orbital decay, creating what theorists call the final parsec problem. Environmental factors play crucial roles in supermassive black hole mergers. Gas accretion disks around each black hole can provide additional mechanisms for energy dissipation through viscous torques and gravitational interactions. When gas flows are present, they can help drive the black holes together more efficiently than stellar interactions alone. The presence of a third supermassive black hole can also assist by providing gravitational perturbations that prevent the binary from stalling. The final approach and merger of supermassive black holes generates gravitational waves with periods ranging from months to years. These extremely low-frequency waves carry enormous amounts of energy, but are currently undetectable with existing instruments. Future space-based gravitational wave detectors, like the Laser Interferometer Space Antenna, will be specifically designed to observe these supermassive mergers. During the actual merger, the energy release dwarfs all other cosmic phenomena. Two supermassive black holes, each containing 1 billion solar masses, can radiate away 50 to 100 million solar masses worth of energy as gravitational waves. This energy output exceeds the total electromagnetic luminosity of the observable universe during the brief merger event. The gravitational waves from such mergers can be detected across cosmological distances, providing windows into galaxy formation and evolution throughout cosmic history. The merger remnant experiences a powerful gravitational wave recoil kick that can reach velocities of several thousand kilometers per second. This kick results from asymmetric gravitational wave emission and can actually eject the merged black hole from its host galaxy entirely, creating a wandering supermassive black hole in intergalactic space. Primordial black hole mergers. Primordial black holes represent a theoretical class of black holes that could have formed in the very early universe, within the first second after the Big Bang. Unlike stellar mass, black holes that form from collapsing stars, primordial black holes would have originated from extremely dense regions of matter that collapsed under their own gravity during the universe's infancy. These objects could have masses ranging from microscopic scales up to thousands of solar masses. The formation of primordial black holes requires density fluctuations in the early universe that were much larger than the average variations observed in the cosmic microwave background radiation. These fluctuations would need to be so extreme that certain regions became dense enough to overcome the expansion of space itself and collapse into black holes. The exact mechanisms that could produce such large density variations remain speculative and depend on poorly understood physics from the universe's first moments. If primordial black holes exist, they would have been distributed throughout space long before the first stars formed. Over billions of years, gravitational interactions would have caused some of these objects to form binary pairs and eventually merge. The merger process would follow the same gravitational wave physics as other black hole mergers, but with some unique characteristics related to their formation, history, and mass distribution. Primordial black hole mergers could occur across an enormous range of mass scales. At the low end, mergers involving black holes with masses comparable to asteroids or mountains would produce high-frequency gravitational waves that current detectors cannot observe. At the high end, mergers of primordial black holes with hundreds or thousands of solar masses could produce signals detectable by current gravitational wave observatories. One distinctive feature of primordial black hole mergers is their potential to occur in environments with little or no surrounding matter. Unlike stellar mass black holes, which form in regions rich with gas and dust, primordial black holes could merge in relatively empty regions of space. This means their mergers might not be accompanied by electromagnetic signals from heated gas or disrupted stellar material, making them detectable only through gravitational waves. The merger rate of primordial black holes depends critically on their abundance and mass distribution, both of which remain highly uncertain. If primordial black holes make up a significant fraction of dark matter, as some theories suggest, their merger rate could be much higher than that of stellar mass black holes. Conversely, if they are rare, their mergers might be virtually undetectable with current technology. When primordial black holes merge, the energy conversion follows the same principles as other black hole mergers, with 1 to 5% of the total mass radiating away as gravitational waves. However, the timescales and frequencies involved can vary dramatically depending on the masses of the merging objects. Lighter primordial black holes would complete their final in-spiral and merger much more rapidly than heavier ones, producing correspondingly higher frequency gravitational waves. Black hole neutron star mergers. When a black hole and neutron star spiral toward each other, they create one of the most complex and violent merger scenarios in the universe. Neutron stars are the collapsed cores of massive stars, containing roughly 1.5 times the mass of our Sun compressed into a sphere only 20 kilometers across. Their material is so dense that a teaspoon would weigh as much as Mount Everest, consisting primarily of neutrons packed together at nuclear density. The merger process begins similarly to black hole systems, with the two objects losing energy through gravitational wave emission and spiraling inward over millions of years. However, the presence of a neutron star introduces fundamentally different physics, because neutron stars have physical surfaces and internal structure. Unlike black holes, which are pure spacetime curvature, as the neutron star approaches the black hole, tidal forces begin to deform its shape. The gravitational gradient across the neutron star becomes increasingly steep, with the side facing the black hole experiencing much stronger gravitational pull than the far side. This differential stretches the neutron star into an elongated shape, similar to how Earth's moon creates ocean tides but vastly more extreme. The critical moment occurs when the neutron star reaches the black hole's tidal disruption radius. At this point, the tidal forces overcome the neutron star's gravitational self-binding, and the star begins to tear apart. The exact distance at which this happens depends on both the black hole's mass and the neutron star's internal structure. For typical systems, disruption occurs when the neutron star approaches within a few hundred kilometers of the black hole. During tidal disruption, the neutron star does not simply fall intact into the black hole. Instead, it gets shredded into streams of ultra-dense matter that spiral around the black hole in highly eccentric orbits. Some of this material falls directly into the black hole, while a significant portion forms an accretion disk of hot, dense matter surrounding the merged object. This disk can contain anywhere from 1/100th to several tenths of a solar mass worth of neutron-rich material. The disrupted neutron star material reaches temperatures of billions of degrees as it spirals inward, becoming hot enough to undergo rapid nuclear reactions. These conditions are perfect for creating heavy elements through the rapid neutron capture process, known as R-process nucleosynthesis. Elements heavier than iron, including gold, platinum, and uranium, are forged in these extreme environments and later ejected into space. The merger produces multiple forms of electromagnetic radiation alongside gravitational waves. The hot accretion disk glows intensely across the electromagnetic spectrum, from radio waves to gamma rays. Some material gets ejected at high velocities, creating expanding shells of radioactive debris that power optical transients called kilonovae. These events can outshine entire galaxies for days or weeks as the newly synthesized heavy elements decay and release energy. The gravitational wave signature of black hole neutron star mergers differs noticeably from pure black hole mergers. The signal shows characteristic features related to the neutron star's tidal deformation and eventual disruption. These signatures allow astronomers to distinguish between different types of mergers and extract information about neutron star internal structure and the equation of state of ultra-dense matter. Neutron star mergers. When two neutron stars spiral toward each other, they create the most element-rich and electromagnetically bright merger events in the universe. Both objects are incredibly dense stellar remnants, each containing roughly 1.5 solar masses compressed into spheres just 20 kilometers across. Their surfaces are solid crusts of atomic nuclei arranged in crystalline lattices, overlying cores of pure neutron matter at densities exceeding that of atomic nuclei. The inspiral phase follows the same gravitational wave physics as other compact object mergers. But neutron star binaries lose energy more rapidly due to their smaller sizes and higher orbital frequencies. As the two neutron stars approach each other, they begin to raise tidal bulges on each other's surfaces, similar to how the moon creates ocean tides on Earth, but millions of times stronger. These tidal deformations extract additional energy from the orbital motion, accelerating the inspiral process. During the final seconds before merger, both neutron stars become severely distorted by mutual tidal forces. Their spherical shapes stretch into elongated ellipsoids, with the pointed ends facing each other. The solid crusts begin to crack and fracture under the extreme tidal stresses, releasing stored elastic energy. At this stage, the neutron stars are orbiting each other hundreds of times per second, with their surfaces moving at significant fractions of the speed of light. The actual collision occurs when the two neutron stars make contact, typically when their centers are separated by roughly 40 kilometers. Unlike black hole mergers, which involve the smooth coalescence of event horizons, neutron star mergers involve the violent collision of solid matter at nuclear densities. The collision creates shock waves that propagate through both objects, heating the material to billions of degrees and disrupting the neutron star structure. The merger outcome depends critically on the total mass of the system. If the combined mass exceeds roughly 2.5 to 3 solar masses, the merged object immediately collapses to form a black hole surrounded by an accretion disk of hot neutron star debris. For lower total masses, the merger can produce a hypermassive neutron star that survives for milliseconds to hours before eventually collapsing. Or, in rare cases, a stable neutron star remnant. During the collision, significant amounts of neutron-rich material get ejected at velocities reaching 10 to 30% the speed of light. This ejecta consists of matter that was heated and accelerated by shock waves, tidal forces, and magnetic field interactions during the merger. The ejected material has an extremely high neutron-to-proton ratio, creating ideal conditions for rapid neutron capture nucleosynthesis. The R-process nucleosynthesis in neutron star merger ejecta produces virtually all elements heavier than iron in the periodic table. Gold, platinum, uranium, and other heavy elements are synthesized within seconds of the merger, as free neutrons are rapidly captured by lighter seed nuclei. A single neutron star merger can produce several Earth masses worth of gold and platinum, along with substantial quantities of other precious metals and radioactive elements. The radioactive decay of these newly synthesized heavy elements powers a distinctive electromagnetic transient called a kilonova. Unlike supernovae, which are powered by the kinetic energy of explosion, kilonovae derive their energy from radioactive decay chains of unstable heavy nuclei. The kilonova emission peaks in the infrared and optical bands over timescales of days to weeks, with the exact light curve depending on the composition and mass of the ejecta. Neutron star mergers also produce short-duration gamma-ray bursts when the merger remnant forms a rapidly rotating black hole with strong magnetic fields. These gamma-ray bursts consist of highly collimated jets of relativistic particles and radiation that can be observed across cosmological distances. The jets carry enormous amounts of energy and can remain active for seconds to minutes after the initial merger. Hierarchical black hole mergers. Hierarchical mergers occur when black holes that formed from previous merger events subsequently merge with other black holes, creating a cascade of increasingly massive objects. This process represents a fundamental pathway for black hole growth throughout cosmic history, and can produce black holes with masses and properties that differ significantly from those formed through direct stellar collapse. The concept of hierarchical mergers emerged from theoretical models of black hole population evolution in dense stellar environments. In globular clusters, galactic nuclei, and other regions with high concentrations of compact objects, the products of initial black hole mergers do not escape the gravitational potential of their host system. Instead, they remain bound and can encounter additional black holes, leading to subsequent merger events. First-generation black holes form directly from stellar collapse and typically have masses ranging from 5 to 50 times that of the Sunday. Their spins are determined by the rotation of their progenitor stars and are generally moderate, rarely exceeding 70% of the maximum possible spin for a black hole. When two first-generation black holes merge, they produce a second-generation black hole with a mass roughly equal to the sum of the original masses minus the energy radiated away as gravitational waves. Second-generation black holes have distinctive properties that reflect their merger origin. Their masses typically range from 20 to 100 solar masses, placing them in a mass range that is difficult to achieve through direct stellar collapse. More importantly, their spins can be significantly higher than first-generation black holes, potentially reaching 90% or more of the maximum theoretical limit. This high spin results from the orbital angular momentum of the merging system being converted into the spin of the final black hole. The process can continue through multiple generations, with second-generation black holes merging with other black holes to produce third-generation objects, and so forth. Each successive generation tends to produce more massive black holes with increasingly high spins. However, the efficiency of this process depends strongly on the dynamics of the host environment and the retention of merger products within the system. Hierarchical mergers can produce black holes with masses exceeding 100 solar masses, entering the regime of intermediate mass black holes. These objects are particularly interesting because they bridge the gap between stellar mass and supermassive black holes, potentially providing seeds for the growth of the supermassive black holes observed at galactic centers. The gravitational wave signatures of hierarchical mergers contain information about their formation history. Higher-generation black holes typically have larger masses and higher spins than first-generation objects, leading to characteristic features in the gravitational wave signal. The inspiral phase shows the effects of spin-orbit coupling, while the merger and ringdown phases reflect the properties of highly spinning black holes. Environmental factors play crucial roles in enabling hierarchical mergers. Dense stellar clusters provide the high encounter rates necessary for repeated mergers, while also retaining the merger products through their deep gravitational potential wells. Gas-rich environments can facilitate black hole encounters through dynamical friction and can also affect the spins of black holes through accretion processes. The rate of hierarchical mergers depends on the formation rate of dense stellar clusters, the initial black hole mass function, and the dynamical evolution of these systems over cosmic time. Current gravitational wave observations suggest that a significant fraction of detected black hole mergers may involve at least one higher-generation black hole, indicating that hierarchical mergers are an important channel for black hole growth in the universe. Eccentric black hole mergers. Eccentric mergers occur when black holes approach each other on highly elliptical orbits rather than the nearly circular paths typical of most gravitational wave detections. These systems spend most of their orbital period at large separations before plunging rapidly toward each other during close approach, creating distinctive gravitational wave signatures that differ dramatically from circular mergers. The formation of eccentric binaries requires specific dynamical processes that cannot circularize the orbit before merger. In dense stellar environments like globular clusters or galactic nuclei, black holes can be scattered into highly eccentric orbits through gravitational interactions with other massive objects. Three-body encounters, where a third black hole or massive star disrupts an existing binary, can pump eccentricity into the system and reduce the merger timescale from billions of years to mere millions. Another pathway involves the Kozai-Leadoff mechanism, where a distant third body causes periodic oscillations in the eccentricity and inclination of an inner binary orbit. As the eccentricity increases during these cycles, the black holes approach closer together at periastron, enhancing gravitational wave emission and accelerating the merger process. This mechanism can operate in hierarchical triple systems or in the presence of massive perturbers like supermassive black holes. The gravitational wave emission from eccentric binaries differs fundamentally from circular systems. Instead of the smooth, monotonic frequency evolution characteristic of circular mergers, eccentric systems produce bursts of gravitational waves during each close approach. These bursts become progressively stronger and more frequent as the orbit decays, creating a distinctive pattern of repeated signals separated by quiet periods. During the highly eccentric phase, the black holes can reach extremely close separations at periastron, while remaining widely separated at apastron. The gravitational wave frequency can vary by orders of magnitude within a single orbit, reaching much higher frequencies during close approach than would be possible for circular orbits at the same average separation. This creates challenges for gravitational wave detection algorithms, which are typically optimized for the smooth frequency evolution of circular mergers. The transition from eccentric to circular orbits occurs when gravitational wave emission removes enough energy to circularize the system. For most eccentric binaries, this circularization happens well before the final merger, typically when the orbital separation reaches a few hundred gravitational radii. However, systems with extreme initial eccentricities can remain noticeably eccentric even during the final in-spiral phase, detectable by gravitational wave observatories. Eccentric mergers can produce stronger gravitational wave signals than their circular counterparts due to the higher orbital velocities achieved during close approach. The peak gravitational wave strain can be enhanced by factors of several compared to circular mergers with the same component masses. This enhancement makes eccentric mergers potentially detectable at greater distances, increasing the observable volume of space for these events. The merger dynamics of eccentric systems also differ from circular cases. The final plunge can occur more rapidly, with less time spent in the strong field regime where post-Newtonian approximations break down. This can affect the accuracy of parameter estimation and the ability to extract information about the black hole properties from gravitational wave observations. Environmental signatures can distinguish eccentric mergers from circular ones. Eccentric binaries formed through dynamical processes in dense stellar environments may retain memory of their formation mechanism in their orbital properties. The distribution of eccentricities and the correlation with other system parameters can provide insights into the astrophysical environments where these mergers occur. Current gravitational wave detectors have limited sensitivity to highly eccentric mergers due to their focus on circular templates and the challenges of searching for signals with rapidly varying frequencies. Future detector improvements and analysis techniques may reveal a population of eccentric mergers that remains largely hidden in current observations. Hyperbolic black hole encounters. Hyperbolic encounters represent the most extreme form of black hole interactions, where two black holes approach each other on unbound, parabolic or hyperbolic trajectories rather than bound elliptical orbits. These encounters occur when black holes pass close enough to each other to emit detectable gravitational waves, but retain sufficient kinetic energy to escape to infinity after their closest approach. The formation of hyperbolic encounters requires specific dynamical conditions where black holes possess high relative velocities compared to their mutual escape velocity. This typically occurs in dense stellar environments where black holes have been accelerated to high speeds through gravitational slingshot interactions with other massive objects. Galactic nuclei, globular clusters, and regions near supermassive black holes provide the necessary conditions for such high-velocity encounters. During a hyperbolic encounter, the two black holes follow trajectories that bring them together from large separations, reach a minimum distance at periastron, and then separate again to infinity. The entire interaction occurs over a much shorter timescale than bound mergers, typically lasting from minutes to hours rather than the millions of years characteristic of circular inspirals. The gravitational wave emission is concentrated into a brief burst during the closest approach phase. The gravitational wave signature of hyperbolic encounters differs dramatically from merger events. Instead of the characteristic chirp pattern of increasing frequency and amplitude, hyperbolic encounters produce a burst-like signal with a rapid rise to maximum amplitude, followed by an equally rapid decay. The peak frequency depends on the minimum separation achieved during closest approach and can reach values comparable to those seen in the final moments of mergers. The energy radiated as gravitational waves during hyperbolic encounters is typically much smaller than in mergers, usually less than 1% of the total system mass energy. However, The peak power output can be comparable to or even exceed that of mergers due to the rapid nature of the interaction. This creates intense but brief gravitational wave bursts that challenge current detection methods optimized for longer duration merger signals. Hyperbolic encounters can result in several possible outcomes depending on the impact parameter and relative velocity of the black holes. At large impact parameters, the black holes experience only minor deflections and emit weak gravitational waves. At intermediate impact parameters, significant orbital energy can be radiated away, potentially converting an initially unbound system into a bound elliptical orbit that will eventually merge. The most extreme hyperbolic encounters occur at very small impact parameters, where the black holes pass within a few gravitational radii of each other. These ultra-close encounters can produce gravitational wave bursts with peak frequencies in the kilohertz range, far higher than typical merger signals. The black holes experience extreme tidal accelerations and can exchange significant amounts of orbital angular momentum, leading to dramatic changes in their spin orientations. Zoom world behavior represents a particularly exotic form of hyperbolic encounter where the black holes execute multiple close approaches before finally separating. This occurs when the orbital energy is very close to the threshold between bound and unbound motion. The system can orbit several times at small separations, producing multiple gravitational wave bursts before either merging or escaping to infinity. The detection of hyperbolic encounters requires specialized search algorithms capable of identifying short-duration burst signals rather than the long-duration chirps of mergers. Current gravitational wave detectors have limited sensitivity to these events due to their brief duration and the challenges of distinguishing them from instrumental glitches and other transient noise sources. Environmental factors strongly influence the rate and properties of hyperbolic encounters. Dense stellar clusters with high-velocity dispersions produce more frequent high-speed encounters, while the presence of supermassive black holes can accelerate stellar mass black holes to the extreme velocities necessary for hyperbolic interactions. The metallicity and age of stellar populations also affect the black hole mass function and encounter rates. Hyperbolic encounters may play important roles in black hole population dynamics by ejecting black holes from dense clusters and redistributing their velocities and spins. They can also serve as precursors to eventual mergers by reducing orbital energies and converting unbound systems into bound binaries that will merge on longer timescales. Kicked black hole mergers. Kicked black hole mergers occur when the gravitational wave recoil from a merger imparts sufficient velocity to the remnant black hole to significantly alter its trajectory or even eject it entirely from its host environment. This recoil phenomenon, also known as gravitational wave kicks, results from the asymmetric emission of gravitational waves during the merger process and can produce remnant velocities ranging from tens to thousands of kilometers per second. The physical mechanism behind gravitational wave kicks involves the conservation of momentum during asymmetric gravitational wave emission. When two black holes with different masses or spins merge, they do not radiate gravitational waves equally in all directions. The net momentum carried away by the gravitational waves must be balanced by an equal and opposite momentum imparted to the merged black hole, causing it to recoil like a rifle firing a bullet. Several factors determine the magnitude and direction of the recoil velocity. Mass ratio asymmetry produces kicks that scale with the square of the mass difference divided by the total mass. For equal mass mergers, this contribution vanishes, but spin asymmetries can generate much larger kicks. When the black hole spins are aligned in the orbital plane and point in opposite directions, the recoil can reach maximum values exceeding 4,000 kilometers per second. The spin-orbit coupling during the final inspiral phase plays a crucial role in determining kick velocities. As the black holes spiral inward, their spins precess due to gravitational interactions, causing the kick direction to change continuously. The final kick magnitude and direction depend on the precise spin orientations at the moment of merger, making kick predictions sensitive to the detailed dynamics of the inspiral phase. Superkicks represent the most extreme form of gravitational wave recoil, occurring when specific spin configurations align to maximize the asymmetric gravitational wave emission. These configurations require the black hole spins to lie in the orbital plane with magnitudes near 70% of the maximum possible value and orientations that are nearly anti-aligned. Under these conditions, the recoil velocity can exceed 5,000 kilometers per second. The astrophysical consequences of gravitational wave kicks depend on the escape velocity of the host environment. In globular clusters with escape velocities of tens of kilometers per second, even modest kicks can eject merged black holes entirely. In galactic nuclei with escape velocities of hundreds to thousands of kilometers per second, only the largest kicks can unbind the remnants. Supermassive black hole mergers in galaxy centers require superkicks to escape their deep gravitational potential wells. Kicked supermassive black holes can have profound effects on their host galaxies. A recoiling central black hole carries away the gravitational binding energy that normally confines the galactic nucleus, causing the central stellar distribution to expand. The displaced black hole can also disrupt star formation in the galactic center and alter the feeding of gas onto the central engine, affecting the galaxy's active galactic nucleus activity. Observational signatures of kicked black holes include off-center quasars, where the active supermassive black hole appears displaced from the galactic center, and recoiling black hole candidates identified through their peculiar velocities relative to their host galaxies. Some candidates show evidence of ongoing accretion despite being displaced from the galactic nucleus, suggesting recent merger and kick events. The population of wandering black holes created by gravitational wave kicks represents a largely hidden component of the universe's black hole census. These objects, ejected from their formation sites, can travel through intergalactic space for billions of years. Intermediate mass black holes, produced by hierarchical mergers in globular clusters, may constitute a significant population of these wandering objects. Kick velocities also affect the retention of black holes in different astrophysical environments, influencing the merger rates observable by gravitational wave detectors. Environments that cannot retain kicked black holes will have lower rates of repeat mergers, while those with deep potential wells can accumulate multiple generations of merger products, enhancing hierarchical merger rates. The measurement of kick velocities from gravitational wave observations requires precise determination of the black hole spins and mass ratio from the in-spiral signal. Current detectors have limited ability to measure kicks directly, but future improvements in sensitivity and parameter estimation may enable direct observation of recoil effects in the gravitational wave data. Electromagnetic counterpart mergers. Electromagnetic counterpart mergers represent black hole merger events that produce observable light across the electromagnetic spectrum, in addition to gravitational waves. While pure black hole mergers typically produce no electromagnetic emission due to the absence of surrounding matter, certain merger scenarios can generate bright electromagnetic signals that provide complementary information to gravitational wave observations. The production of electromagnetic counterparts requires the presence of matter in the vicinity of the merging black holes. This material can exist in several forms, including accretion disks around one or both black holes, circumbinary disks that surround the entire binary system, or ambient gas and dust in the merger environment. When the merger occurs, the violent gravitational dynamics can shock heat this material, accelerate it to relativistic speeds, or trigger magnetic field reconnection events that produce electromagnetic radiation. Active galactic nucleus environments provide ideal conditions for electromagnetic counterparts to black hole mergers. When supermassive black holes at galactic centers merge, they are often surrounded by dense accretion disks and broadline regions containing ionized gas. The merger can disrupt these structures, creating shock waves that propagate through the gas and produce optical, ultraviolet, and X-ray emission. The disruption can also trigger changes in the accretion rate onto the merged black hole, causing variations in the quasar luminosity. Stellar mass black hole mergers in dense stellar environments can produce electromagnetic counterparts through several mechanisms. If the merger occurs within or near a stellar envelope, the gravitational wave energy can shock heat the stellar material, creating a transient optical source. Alternatively, if one of the black holes has a small accretion disk from a companion star, the merger can disrupt this disk and produce X-ray and gamma-ray emission. The most dramatic electromagnetic counterparts occur when black hole mergers are associated with gamma-ray bursts. Some theoretical models suggest that the merger of two black holes with aligned spins and surrounding magnetic fields can launch relativistic jets that produce short-duration gamma-ray bursts. These events would appear as coincident gravitational wave and gamma-ray signals, providing unprecedented insights into the merger physics. Tidal disruption events can also accompany black hole mergers when a star passes close to the merging system during the final in-spiral phase. The extreme tidal forces can tear the star apart, creating streams of stellar debris that fall onto the black holes and produce bright electromagnetic flares. These events would appear as optical and X-ray transients occurring simultaneously with the gravitational wave merger signal. The electromagnetic emission from merger counterparts typically evolves on much longer timescales than the gravitational wave signal. While the gravitational waves last for seconds to minutes, the electromagnetic counterparts can persist for days to years as shocked material cools and expands. This extended emission provides opportunities for detailed follow-up observations with optical, X-ray, and radio telescopes. Kilonovae represent a special class of electromagnetic counterparts associated with neutron star mergers. But similar phenomena might occur in black hole mergers under specific conditions. If a black hole merger ejects neutron-rich material through magnetic field interactions or disk winds, the radioactive decay of heavy elements synthesized in this material could power a kilonova-like transient. The detection of electromagnetic counterparts to black hole mergers requires rapid follow-up observations triggered by gravitational wave alerts. The electromagnetic signals are often faint and fade quickly, necessitating immediate response from ground-based and space-based telescopes. The localization accuracy of gravitational wave detectors limits the efficiency of these searches, as large sky areas must be surveyed to find the counterpart. Multi-messenger astronomy, combining gravitational waves and electromagnetic observations, provides powerful constraints on merger physics that neither signal alone can achieve. The electromagnetic counterparts reveal information about the merger environment, the presence of magnetic fields, and the properties of any ejected material, while the gravitational waves provide precise measurements of the black hole masses and spins. The rate of electromagnetic counterparts to black hole mergers remains highly uncertain due to the unknown fraction of mergers that occur in environments with sufficient surrounding matter. Current estimates suggest that only a small percentage of stellar mass black hole mergers will produce detectable electromagnetic signals, while supermassive black hole mergers in active galactic nuclei may have higher counterpart rates. Merger detection methods. Merger detection methods. Gravitational wave detection represents the primary method for observing black hole mergers. Utilizing laser interferometry to measure the minute distortions in spacetime caused by passing gravitational waves. Ground-based detectors like the Laser Interferometer Gravitational Wave Observatory consist of two perpendicular arms, each several kilometers long, with laser beams traveling back and forth between mirrors at the ends. When a gravitational wave passes through the detector, it alternately stretches and compresses space in perpendicular directions, causing tiny changes in the arm lengths that can be measured with extraordinary precision. The sensitivity of gravitational wave detectors reaches phenomenal levels, capable of detecting length changes smaller than 1/10,000th the width of a proton. This requires sophisticated isolation systems to eliminate vibrations from seismic activity, thermal fluctuations, and quantum noise. Multiple detectors operating simultaneously provide confirmation of signals and enable triangulation to determine the source direction, though localization accuracy remains limited to regions spanning hundreds of square degrees on the sky. Matched filtering techniques compare observed data streams with theoretical templates that predict the gravitational wave signatures of different merger scenarios. These templates incorporate the complex physics of general relativity, including the effects of black hole spins, mass ratios, and orbital eccentricities. The detection process involves searching through millions of template waveforms to find the best match with the observed signal, allowing extraction of the black hole properties and merger parameters. Electromagnetic follow-up observations attempt to identify optical, X-ray, radio, or gamma-ray counterparts to gravitational wave events. Rapid alert systems notify astronomical observatories within minutes of gravitational wave detections, triggering coordinated searches across the electromagnetic spectrum. These searches face significant challenges due to the large sky areas that must be surveyed and the typically faint and rapidly fading nature of electromagnetic counterparts. Space-based gravitational wave detectors will extend merger observations to much lower frequencies than ground-based instruments can access. The Laser Interferometer Space Antenna will consist of 3 spacecraft, separated by millions of kilometers, forming a triangular detector sensitive to gravitational waves, with periods ranging from seconds to hours. This frequency range will enable detection of supermassive black hole mergers and provide years of advance warning before stellar mass binaries merge. Pulsar timing arrays use networks of precisely timed millisecond pulsars as cosmic clocks to detect very low-frequency gravitational waves from supermassive black hole mergers. These arrays monitor the arrival times of pulsar signals over many years, searching for correlated timing variations that would indicate passing gravitational waves. The method is sensitive to gravitational waves, with periods of months to years, complementing other detection techniques. Indirect detection methods infer the occurrence of black hole mergers through their astrophysical consequences rather than direct observation of gravitational waves. These include searches for recoiling black holes displaced from galactic centers, disrupted stellar distributions around merged supermassive black holes, and chemical signatures of heavy element production in neutron star mergers that may also apply to certain black hole merger scenarios. Multi-messenger astronomy combines gravitational wave detections with observations across the electromagnetic spectrum, and potentially with neutrino detectors. This approach provides comprehensive information about merger events that no single detection method can achieve alone. The combination of gravitational wave timing with electromagnetic observations can break degeneracies in parameter estimation and provide independent measurements of cosmological parameters. Machine learning algorithms increasingly supplement traditional matched filtering techniques for gravitational wave detection and parameter estimation. Neural networks trained on simulated merger signals can identify weak signals buried in detector noise and rapidly estimate merger parameters. These methods show particular promise for detecting signals from eccentric mergers and other non-standard scenarios that are difficult to template with traditional approaches. Future detector improvements will dramatically enhance merger detection capabilities through increased sensitivity, expanded frequency ranges, and improved sky localization. Third-generation ground-based detectors will achieve sensitivities 10 times better than current instruments, enabling detection of mergers throughout the observable universe and providing precise measurements of merger rates as functions of cosmic time and environment. Merger rate evolution. The rate of black hole mergers has evolved dramatically throughout cosmic history, reflecting changes in star formation, stellar evolution, and the growth of structure in the universe. During the early universe, roughly 10 to 12 billion years ago, star formation rates peaked at levels 10 times higher than today, creating the massive stars that would eventually collapse into the black holes we observe merging in the present epoch. The delay time between the formation of massive stellar binaries and their eventual merger as black holes spans hundreds of millions to billions of years. This delay results from the time required for stellar evolution, supernova explosions, and the subsequent gravitational wave-driven inspiral of the resulting black hole binary. Consequently, the black hole mergers detected today originated from stars that formed during the universe's peak star formation era, when galaxies were more gas-rich and actively forming stars. Metallicity evolution plays a crucial role in determining merger rates across cosmic time. Low metallicity stars, which were more common in the early universe, can retain more mass during their evolution and produce more massive black holes. They also experience weaker stellar winds, making it easier for close binary systems to survive the stellar evolution process and eventually merge as black holes. As the universe has evolved and become more metal-rich, the efficiency of black hole binary formation has likely decreased. The merger rate in different environments varies by orders of magnitude depending on stellar density, metallicity, and dynamical processes. Globular clusters, with their high stellar densities and low metallicities, can produce merger rates hundreds of times higher per unit stellar mass than typical galactic fields. Young star clusters and galactic nuclei also show enhanced merger rates due to dynamical interactions that can form black hole binaries and accelerate their merger timescales. Current gravitational wave observations suggest stellar mass black hole merger rates of approximately 10 to 100 events per cubic gigaparsec per year in the local universe. However, this rate likely represents only a fraction of the peak merger rate that occurred several billion years ago, when the universe was younger and more actively forming the massive stars that produce merging black holes today. Supermassive black hole merger rates follow the hierarchical growth of cosmic structure, with peak rates occurring during the era of major galaxy mergers roughly 8 to 10 billion years ago. As galaxies merge to form larger structures, their central supermassive black holes were brought together, eventually merging after complex dynamical evolution. The current rate of supermassive black hole mergers is much lower than during this peak epoch. Population synthesis models attempt to predict merger rates by simulating the evolution of stellar populations from formation through black hole merger. These models incorporate stellar evolution, physics, binary interactions, supernova kicks, and gravitational wave and spiral to predict the numbers and properties of merging black holes. Different assumptions about stellar physics and binary evolution can lead to merger rate predictions that vary by factors of 10 or more. The observed merger rate provides constraints on uncertain aspects of stellar and binary evolution. The masses and spins of merging black holes encode information about their formation channels, while the overall merger rate constrains the efficiency of black hole binary formation and survival. Discrepancies between predicted and observed rates highlight gaps in our understanding of stellar evolution in binary systems. Environmental dependence of merger rates reflects the complex interplay between stellar formation, evolution, and dynamics. Dense stellar environments can enhance merger rates through dynamical formation of black hole binaries, but they can also disrupt existing binaries through gravitational interactions. The balance between these competing effects determines the net merger rate in different astrophysical environments. Redshift evolution of merger rates will become measurable as gravitational wave detectors improve and observe mergers at greater distances. The rate evolution encodes information about cosmic star formation history, the initial mass function of stars, and the time delays between star formation and black hole merger. Future observations will test models of cosmic evolution and provide insights into the formation of the first black holes in the universe. Selection effects significantly influence the observed merger rate, as current detectors are most sensitive to nearby, high-mass mergers. The true merger rate includes many low-mass systems and distant events that remain below the detection threshold. As detector sensitivity improves, the observed merger rate will increase dramatically, revealing the full population of merging black holes throughout the universe. Primordial black hole merger rates, if these objects exist, would follow different evolutionary patterns than stellar mass black holes. Primordial black holes formed in the early universe would begin merging immediately after formation, with rates that depend on their initial clustering and the expansion of the universe. The merger rate would peak early in cosmic history and decline as the objects become more widely separated by cosmic expansion. Future merger scenarios. The next generation of gravitational wave detectors will revolutionize black hole merger observations by detecting events across the entire observable universe and revealing merger populations that remain hidden from current instruments. Third-generation ground-based detectors like the Einstein Telescope and Cosmic Explorer will achieve sensitivities 10 times better than current facilities, enabling detection of stellar mass black hole mergers out to redshifts exceeding 10 when the universe was less than 500 million years old. These advanced detectors will observe the formation and merger of the first black holes in cosmic history, providing direct insights into the earliest epochs of star formation and the seeding of supermassive black holes. The merger rate at high redshifts will reveal how quickly massive stars formed and evolved in the primordial universe, testing models of population 3 star formation and the initial mass function of the first stellar generation. Space-based gravitational wave observatories will open entirely new windows into black hole mergers by accessing the millihertz frequency range where supermassive black hole mergers produce their strongest signals. The Laser Interferometer Space Antenna will detect supermassive black hole mergers years before they occur, providing unprecedented advance warning and enabling detailed electromagnetic follow-up campaigns to study the merger environment and aftermath. Multi-band gravitational wave astronomy will track individual black hole binaries across multiple frequency ranges as they evolve from wide orbits detectable by space-based instruments to the final merger observable by ground-based detectors. This continuous monitoring will provide complete merger histories and enable precise tests of general relativity across vastly different gravitational field strengths and orbital velocities. The merger of intermediate mass black holes will become routinely detectable with next-generation instruments, filling the gap between stellar mass and supermassive black hole observations. These events will reveal the formation mechanisms of intermediate mass black holes and their role in seeding supermassive black holes at galactic centers. The detection rate of intermediate mass mergers will constrain models of black hole growth in dense stellar environments. Eccentric and hyperbolic black hole encounters will be detectable in large numbers, revealing the importance of dynamical formation channels in dense stellar environments. The orbital eccentricity distribution of merging black holes will distinguish between different formation scenarios and provide insights into the dynamical evolution of black hole populations in globular clusters and galactic nuclei. Primordial black hole mergers, if they exist, will be detectable across a wide range of masses, from asteroid-scale objects to intermediate mass black holes. The merger rate and mass distribution of primordial black holes will constrain models of the early universe and potentially reveal the nature of dark matter. High-frequency gravitational wave detectors may be required to observe the smallest primordial black hole mergers. The merger of black holes with exotic compact objects like boson stars or gravastars will be distinguishable from conventional black hole mergers through their distinctive gravitational wave signatures. These observations could reveal new physics beyond general relativity, or confirm the existence of alternative compact object types predicted by various theoretical models. Environmental effects on black hole mergers will become measurable through correlations between merger properties and host galaxy characteristics. The metallicity, star formation history, and dynamical environment of merger host galaxies will be determinable through electromagnetic follow-up observations, enabling detailed studies of how environment influences black hole formation and merger rates. Cosmological applications of black hole merger observations will provide independent measurements of the Hubble constant and other cosmological parameters. The standard SIREN method uses gravitational wave distance measurements combined with electromagnetic redshift determinations to constrain cosmic expansion rates. Large samples of merger events will enable precision cosmology tests and potentially resolve current tensions in cosmological parameter measurements. The merger of supermassive black holes in the local universe will be detectable years in advance, enabling comprehensive, multi-wavelength monitoring campaigns. These observations will reveal the electromagnetic signatures of supermassive black hole mergers, test predictions for environmental disruption, and measure gravitational wave recoil effects through long-term monitoring of the merger remnants. Population studies of black hole mergers will reveal the complete mass and spin distributions of black holes throughout cosmic history. The evolution of these distributions with redshift will constrain stellar evolution models, binary interaction physics, and the formation channels that produce merging black holes. Rare merger events involving the most massive stellar mass black holes will test the upper limits of stellar collapse. Merger physics extremes. The most extreme black hole mergers involve objects at the theoretical limits of mass, spin, and energy release, creating conditions where the fundamental forces of nature operate at their maximum intensities. When two maximally spinning black holes, each rotating at 99% of their theoretical limit, merge together, they create spacetime distortions so severe that the very concepts of space and time become stretched beyond normal comprehension. The energy release during the most powerful black hole mergers exceeds the total electromagnetic output of all stars in the observable universe combined. When two supermassive black holes, each containing 10 billion solar masses, collide and merge, they can convert more than 1 billion solar masses worth of material into pure gravitational wave energy in less than 1 second. This energy density approaches the theoretical limits imposed by general relativity and represents the most efficient conversion of mass to energy possible in the universe. The gravitational field strengths near merging black holes reach values where spacetime curvature becomes so extreme that tidal forces can accelerate particles to significant fractions of the speed of light over distances of mere kilometers. During the final milliseconds before merger, the gravitational acceleration at the event horizon can exceed 10 to the 15th meters per second squared, more than 100 trillion times stronger than Earth's surface gravity. Temperature extremes in the immediate vicinity of merging black holes can reach values exceeding 1 trillion degrees Kelvin, when surrounding matter gets shock heated by the violent gravitational dynamics. This temperature is roughly 100,000 times hotter than the core of the Sun and approaches the energy scales where particle physics enters regimes that cannot be reproduced in terrestrial laboratories. The rotational velocities of maximally spinning black holes approach the speed of light at their event horizons, with surface velocities reaching 299 million meters per second. When two such rapidly rotating objects merge, the conservation of angular momentum can create merger remnants that spin faster than either original black hole, temporarily exceeding the theoretical maximum before settling into a stable configuration through gravitational wave emission. Magnetic field strengths in the environments surrounding merging black holes can reach values of 10 to the 15th Tesla, more than 1 trillion times stronger than the most powerful magnetic fields achievable on Earth. These extreme magnetic fields can accelerate charged particles to ultra-relativistic energies and potentially trigger the formation of relativistic jets that extend across galactic distances. The spacetime metric distortions during black hole mergers create regions where the normal relationships between cause and effect become severely altered. Light cones, which define the boundaries of causal influence, become so tilted that events can influence their own past through closed time-like curves that exist briefly during the merger process, before being eliminated as the system settles into its final state. Gravitational wave amplitudes during the peak merger phase can reach strain values of 10 to the minus 18 at distances of 100 megaparsecs, representing fractional length changes that are detectable despite being smaller than 1/10,000th the width of a proton. At the source, these strain amplitudes approach unity, meaning that spacetime itself is being stretched and compressed by factors of 2 or more. The power output during peak gravitational wave emission can exceed 10 to the 56 watts, a value so enormous that it defies comprehension through everyday analogies. This power output exceeds the combined electromagnetic luminosity of all stars, galaxies, and quasars in the observable universe by factors of millions, making merging black holes temporarily the most luminous objects in existence. Quantum effects near merging black holes operate in regimes where the uncertainty principle interacts with extreme gravitational fields to create particle production rates that can approach the theoretical maximum allowed by quantum field theory. Virtual particle pairs get separated by tidal forces so extreme that they become real particles, potentially creating observable signatures of quantum gravity effects. The information processing capacity of merging black holes reaches theoretical limits imposed by the holographic principle, where the event horizon surface area determines the maximum amount of information that can be encoded in the system. During merger, the rapid changes in horizon area create information processing rates that approach the fundamental limits imposed by quantum mechanics and thermodynamics. Spacetime topology changes during black hole mergers involve the coalescence of separate event horizons into a single, larger horizon through processes that temporarily create regions of spacetime with exotic geometric properties. The merger process involves topological transitions that are among the most extreme geometric transformations possible within the framework of general relativity. The final ringdown phase of black hole mergers involves the newly formed black hole oscillating in its fundamental vibrational modes, similar to a struck bell, but with frequencies determined by the black hole's mass and spin rather than material properties. These oscillations represent the space-time equivalent of sound waves, propagating through the fabric of reality itself at the speed of light. Stellar black holes. Stellar black holes form when the most massive stars in the universe reach the end of their lives and collapse under their own gravity. These cosmic monsters represent the first and most common type of black hole, created through one of the most violent processes in nature. When a star at least 20 times heavier than our Sun exhausts its nuclear fuel, it can no longer maintain the outward pressure needed to counteract its own gravitational pull. The star's core caves in on itself in a catastrophic event called gravitational collapse. This process happens incredibly quickly, with the core shrinking from thousands of kilometers across to just a few dozen kilometers in less than a second. During this collapse, gravity overwhelms every other fundamental force in the universe. The electromagnetic force that keeps atoms intact, the strong nuclear force that binds protons and neutrons together, and the weak nuclear force all become powerless against the crushing weight of gravity. Matter gets compressed to densities so extreme that a teaspoon of this material would weigh as much as Mount Everest. The result is an object that weighs between 3 and 100 times the mass of our Sun, yet fits into a sphere no larger than a typical city. To understand this scale, imagine compressing the entire mass of dozens of suns into an area smaller than Manhattan. The gravitational field becomes so intense that it warps the fabric of spacetime itself, creating a region where the normal rules of physics break down. Around every stellar black hole exists an invisible boundary called the event horizon. This represents the point of no return, where the gravitational pull becomes so strong that nothing, not even light traveling at 300 million meters per second, can escape. The size of this boundary depends on the black hole's mass. A black hole with 10 times the mass of the Sun would have an event horizon roughly 30 kilometers across. Despite being invisible by definition, astronomers can detect stellar black holes through their gravitational effects on nearby objects. When a stellar black hole exists in a binary system with a normal star, it can steal gas and material from its companion. This stolen matter doesn't fall straight into the black hole. Instead, it forms a swirling disk called an accretion disk, where friction heats the material to millions of degrees. This superheated gas glows brilliantly in X-rays, creating a beacon that telescopes can detect from thousands of light-years away. Scientists estimate that our galaxy alone contains millions of stellar black holes, most drifting silently through space without any nearby stars to feed on. These dormant black holes remain completely invisible unless they happen to pass in front of a distant star, causing the star's light to bend and brighten in an effect called gravitational microlensing. The discovery of gravitational waves by the LIGO and Virgo detectors has opened a new window into stellar black holes. When two stellar black holes spiral into each other and merge, they create ripples in spacetime that travel across the universe at the speed of light. Intermediate black holes. Intermediate black holes represent one of the most puzzling mysteries in modern astrophysics. These objects occupy the middle ground between stellar black holes and supermassive black holes, weighing anywhere from a few hundred to roughly 100,000 times the mass of our Sun. Despite decades of searching, they remain some of the most elusive objects in the universe. The mystery of intermediate black holes lies not just in their rarity, but in what their existence could reveal about how black holes grow and evolve. Stellar black holes form from collapsing stars and typically weigh no more than a few dozen solar masses. Supermassive black holes, found at the centers of galaxies, can weigh millions or billions of times more than our Sun. The gap between these two categories seems too large to bridge through normal growth processes. If a stellar black hole tried to grow into a supermassive black hole by consuming nearby matter, it would take far longer than the current age of the universe. Yet, observations show that supermassive black holes already existed when the universe was less than 1 billion years old. Intermediate black holes could provide the missing link, serving as the seeds that allowed supermassive black holes to grow so quickly in the early universe. Finding intermediate black holes proves incredibly difficult because they lack the obvious signatures of their larger and smaller cousins. Unlike supermassive black holes, which often power brilliant quasars that can be seen across billions of light-years, intermediate black holes are typically quiet and dim. They don't consume vast amounts of matter, so they don't produce the dramatic light shows that make supermassive black holes easy to spot. Scientists search for intermediate black holes by looking for their gravitational effects on surrounding stars and gas. In dense star clusters, where hundreds of thousands of stars are packed into a relatively small region, an intermediate black hole at the center would influence the motions of nearby stars. By carefully mapping the orbits of these stars, astronomers can infer the presence of a massive invisible object. One promising hunting ground is globular clusters, ancient collections of stars that orbit around galaxies. Some globular clusters show evidence of central mass concentrations that could be intermediate black holes. The globular cluster 47 Tucanae, for example, contains something with several thousand solar masses at its center, based on the way stars move in the cluster's core. Dwarf galaxies also provide potential homes for intermediate black holes. These small galaxies, which contain only a fraction of the stars found in larger galaxies like the Milky Way, sometimes show signs of central black holes that are neither stellar nor supermassive in size. The galaxy HLX-1, located about 290 million light-years from Earth, appears to host a black hole weighing roughly 20,000 solar masses. Occasionally, intermediate black holes reveal themselves through violent events. When such a black hole tears apart and consumes a passing star, the resulting burst of X-rays can be detected by space-based telescopes. These tidal disruption events provide some of the strongest evidence for intermediate black holes, though they occur rarely and unpredictably. Supermassive black holes. Supermassive black holes represent the true giants of the cosmic hierarchy, containing masses that range from millions to billions of times that of our Sunday, these titanic objects don't lurk in random corners of space like their smaller stellar cousins. Instead, they occupy positions of supreme importance at the hearts of galaxies, where they serve as invisible anchors that help shape and control the evolution of entire galactic systems. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A star, contains approximately 4 million solar masses, compressed into a region smaller than the orbit of Mercury. Despite being 26,000 light-years away from Earth, its gravitational influence is so powerful that astronomers can observe individual stars whipping around it at incredible speeds. Some of these stars complete full orbits in just 16 years, reaching velocities of up to 5,000 kilometers per second at their closest approach. The scale of supermassive black holes defies easy comprehension. While stellar black holes might be compared to cities in size, supermassive black holes can be larger than our entire solar system. The supermassive black hole in the galaxy Messier 87 contains more than 6 billion solar masses. In 2019, this monster became the first black hole ever directly imaged by the Event Horizon Telescope, appearing as a glowing ring of superheated gas surrounding a dark central shadow. The formation of supermassive black holes presents one of the greatest puzzles in modern astrophysics. No single star could ever grow large enough to collapse into an object containing millions of solar masses. Several competing theories attempt to explain their origins. One possibility suggests they began as smaller black holes that grew over billions of years by consuming stars, gas, and other black holes. Another theory proposes that in the early universe, massive clouds of primordial gas collapsed directly into supermassive black holes without ever forming stars. The mystery deepens when considering how quickly these giants must have grown. Observations reveal supermassive black holes already existed when the universe was less than 1 billion years old, leaving insufficient time for gradual growth from stellar mass seeds. This timeline problem has led some scientists to propose that supermassive black holes formed from intermediate mass black holes or through other exotic mechanisms in the early cosmos. Supermassive black holes don't simply sit passively at galactic centers. They actively influence their surroundings through a process called accretion. As matter spirals toward the black hole, gravitational forces compress and heat it to temperatures exceeding millions of degrees. This superheated material forms an accretion disk that glows brilliantly across the electromagnetic spectrum. The energy released during accretion can outshine the combined light of all stars in the host galaxy. When supermassive black holes feed actively, they become visible as quasars, among the most luminous objects in the universe. These cosmic beacons can be detected from billions of light-years away, serving as lighthouses that illuminate the early universe. The energy output from an actively feeding supermassive black hole can drive powerful winds that blow gas out of the galaxy, regulating star formation and sculpting galactic evolution over cosmic time. Every large galaxy observed appears to contain a supermassive black hole at its center, suggesting a fundamental connection between black hole growth and galaxy formation. Primordial black holes. Primordial black holes represent a completely different category of cosmic objects that may have formed not from collapsing stars, but during the first moments after the Big Bang itself. Unlike stellar or supermassive black holes, which require millions or billions of years to develop, primordial black holes could have emerged when the universe was less than 1 second old, making them potentially the oldest structures in existence. In the earliest moments of cosmic history, the universe existed in a state of extreme density and temperature that defies normal comprehension. During this primordial epoch, tiny fluctuations in the fabric of spacetime itself could have concentrated matter so intensely that gravity immediately crushed it into black holes. These density variations, possibly quantum in nature, would have created pockets where matter became compressed beyond any threshold that normal physics could resist. The theoretical size range of primordial black holes spans an almost incomprehensible spectrum. Some could be smaller than individual atoms, yet contain masses measured in kilograms or tons. Others might rival asteroids or even mountains in weight while occupying spaces no larger than grains of sand. To visualize this extreme compression, imagine squeezing the entire mass of Mount Everest into a region smaller than a proton, creating an object with gravitational effects far exceeding anything found in normal matter. Scientists have become intensely interested in primordial black holes because they could potentially solve one of cosmology's greatest mysteries: the nature of dark matter. Astronomical observations consistently show that galaxies rotate and move in ways that cannot be explained by the visible matter they contain. Something invisible must be providing the additional gravitational pull needed to hold galactic structures together. But decades of searching have failed to identify what this dark matter actually is. If primordial black holes exist in sufficient numbers, they could account for some or all of the missing dark matter in the universe. Unlike exotic particles that interact only weakly with normal matter, primordial black holes would be purely gravitational objects, invisible, simply because they emit no light rather than because they belong to some unknown category of particle physics. The implications extend far beyond dark matter. Primordial black holes could also explain how supermassive black holes grew so large so quickly in the early universe. Instead of starting from stellar mass seeds that would take too long to reach billions of solar masses, supermassive black holes could have begun as much more massive primordial seeds, giving them a significant head start in their growth process. Detecting primordial black holes presents enormous challenges because of their potentially tiny sizes and lack of nearby matter to consume. Scientists search for them through several indirect methods. Gravitational microlensing occurs when a primordial black hole passes between Earth and a distant star, causing the star's light to brighten temporarily as the black hole's gravity acts like a cosmic magnifying glass. Another detection method involves looking for the effects of Hawking radiation. According to theoretical physics, all black holes slowly evaporate by emitting particles, with smaller black holes evaporating faster than larger ones. Primordial black holes with masses similar to asteroids would be completing their evaporation process right now, potentially creating detectable bursts of high-energy particles and radiation. Quantum black holes. Quantum black holes exist at the intersection of two fundamental theories that normally operate in completely separate realms of physics. Einstein's general relativity governs the behavior of massive objects and the curvature of spacetime on cosmic scales, while quantum mechanics describes the probabilistic and uncertain world of subatomic particles. When these two frameworks collide at the smallest possible scales, they produce the theoretical concept of quantum black holes. These hypothetical objects would exist at what physicists call the Planck scale, named after physicist Max Planck, who first identified the fundamental limits of measurement in nature. The Planck length measures approximately 10 to the negative 35th meters, a distance so small that it makes atoms appear gigantic by comparison. A hydrogen atom is roughly 10 trillion times larger than the Planck length, illustrating just how incredibly tiny this scale truly is. At the Planck scale, the normal concepts of space and time begin to break down. The smooth fabric of spacetime that Einstein described becomes a seething foam of quantum fluctuations, where virtual particles constantly pop into existence and annihilate each other in time frames shorter than any possible measurement. In this quantum realm, a black hole would represent the ultimate meeting point between gravity and quantum uncertainty. A quantum black hole would contain a mass compressed into a region at or near the Planck length. Despite being unimaginably small, such an object would still possess the fundamental properties that define all black holes: an event horizon beyond which nothing can escape, and a central singularity where density becomes infinite. However, quantum effects would dominate the behavior of such tiny black holes in ways that larger black holes never experience. The most significant quantum effect affecting these microscopic black holes is Hawking radiation, named after physicist Stephen Hawking, who first described the phenomenon. According to quantum field theory, the intense gravitational field near a black hole's event horizon causes pairs of virtual particles to separate, with one particle falling into the black hole while the other escapes as real radiation. This process causes all black holes to slowly evaporate over time. For stellar and supermassive black holes, Hawking radiation occurs so slowly that these objects would take longer than the current age of the universe to evaporate completely. A black hole with the mass of our Sun would require 10 to the 67th years to disappear entirely. However, quantum black holes would evaporate almost instantaneously, releasing their entire mass energy in a brilliant flash lasting only 10 to the negative 43rd seconds. Some theoretical physicists speculate that quantum black holes might have formed during the extremely high-energy conditions present immediately after the Big Bang. Others wonder whether modern particle accelerators like the Large Hadron Collider could create them during high-energy collisions between protons. However, even if such creation were possible, the resulting quantum black holes would vanish so quickly that detecting them would prove nearly impossible with current technology. The study of quantum black holes serves a purpose beyond mere theoretical curiosity. These objects represent a crucial testing ground for theories that attempt to unify general relativity with quantum mechanics into a single framework called quantum gravity. Rogue black holes. Rogue black holes represent one of the most terrifying possibilities in the cosmos. Invisible gravitational monsters drifting through space without any fixed location or predictable orbit. Unlike supermassive black holes that remain anchored at galactic centers or stellar black holes that stay roughly where their parent stars died, rogue black holes wander freely through the universe, making them nearly impossible to detect until they interact with nearby matter or pass close to other objects. These cosmic wanderers form through several violent processes that can eject black holes from their original locations. When massive stars explode in asymmetric supernovae, the uneven distribution of energy can kick the resulting black hole away from its birthplace at speeds reaching hundreds of kilometers per second. Binary black hole systems can also create rogues when gravitational interactions with a third black hole eject one member of the pair, sending it careening through space at tremendous velocity. Galactic collisions provide another mechanism for creating rogue black holes. When two galaxies merge, their central supermassive black holes eventually spiral toward each other in a cosmic dance that can last millions of years. If a third supermassive black hole enters this system, the complex gravitational interactions can slingshot one of the black holes completely out of the merged galaxy, creating a rogue supermassive black hole wandering through intergalactic space. The most frightening aspect of rogue black holes lies in their stealth. Since black holes emit no light of their own, a rogue black hole approaching our solar system would remain completely invisible until its gravitational effects became apparent. By that time, the disruption to planetary orbits and the structure of the solar system could already be underway. Even a stellar mass rogue black hole passing through the outer regions of our solar system could destabilize the orbits of planets and send comets from the Oort cloud cascading toward the inner solar system. Scientists estimate that millions of rogue black holes may be drifting through the Milky Way galaxy at any given time. Most of these would be stellar mass black holes ejected from their birth sites by supernova kicks. But some could be intermediate mass or even supermassive rogues expelled from other galaxies during cosmic collisions. The vast majority remain completely undetected, invisible ghosts moving through the darkness between stars. Detecting rogue black holes requires indirect methods that rely on their gravitational effects rather than any light they might emit. Gravitational microlensing provides the most promising detection technique. When a rogue black hole passes between Earth and a distant star, its gravity acts like a cosmic magnifying glass, temporarily brightening the background star in a characteristic pattern that reveals the presence of the intervening black hole. In 2022, astronomers announced the first confirmed detection of a rogue black hole using this microlensing technique. Located approximately 5,000 light-years from Earth, this stellar mass black hole revealed itself by distorting the light from a more distant star over several months. The discovery confirmed that rogue black holes do indeed exist and wander through our galaxy, though determining their exact numbers and trajectories remains extremely challenging. The unpredictable nature of rogue black holes makes them particularly unsettling. Unlike other cosmic threats that follow predictable orbits or remain in known locations, rogues could appear anywhere at any time. Magnetars. Magnetars represent the most magnetically powerful objects known to exist in the universe, possessing magnetic fields so intense they fundamentally alter the behavior of matter and energy in their vicinity. These exotic stellar remnants form when the most massive stars undergo core collapse during supernova explosions. But unlike typical neutron stars, magnetars develop magnetic fields that are quadrillions of times stronger than Earth's protective magnetic field. The formation process of magnetars begins similarly to other neutron stars, with a massive star exhausting its nuclear fuel and collapsing under its own gravity. However, magnetars likely form from stars that were rotating extremely rapidly before their collapse. or from binary systems where complex interactions amplify the magnetic field during the collapse process. The exact mechanism remains partially mysterious, but the result is a neutron star with a magnetic field measuring between 10 to the 14th and 10 to the 15th Gauss. To understand the incredible strength of these magnetic fields, consider that Earth's magnetic field measures roughly half a Gauss, while the strongest magnetic fields created in laboratories reach about 45 Tesla, or 450,000 Gauss. A magnetar's field is so powerful that it could erase the magnetic strip on a credit card from a distance of 100,000 kilometers and would be lethal to human life from a distance of 1,000 kilometers due to the disruption of biological processes. The intense magnetic field of a magnetar affects the very structure of atoms in its vicinity. In the strongest regions near the magnetar's surface, the magnetic field becomes so powerful that it stretches hydrogen atoms into elongated shapes, with the electron orbits becoming highly distorted. This creates exotic forms of matter that cannot exist anywhere else in the universe, where the normal rules of atomic physics break down under the influence of extreme magnetism. Magnetars announce their presence through sudden, violent outbursts of high-energy radiation. These starquakes occur when the magnetar's crust, made of crystallized nuclear matter, cracks under the enormous stress created by the twisting magnetic field lines. When the crust fractures, it releases energy equivalent to all the earthquakes on Earth over several million years, but concentrated into a burst lasting only a few seconds. The most powerful magnetar flare ever recorded occurred in December 2004, when magnetar SGR 1806-20 unleashed a burst of gamma rays and X-rays so intense that it temporarily blinded satellites throughout the solar system and caused measurable changes in Earth's upper atmosphere. This flare, originating from a magnetar located 50,000 light-years away, released more energy in 1/10 of a second than our Sun produces in 100,000 years. The magnetic field lines of magnetars extend far beyond the neutron star itself, creating a magnetosphere that can stretch for thousands of kilometers. Within this region, charged particles become trapped and accelerated to nearly the speed of light, creating beams of radiation that sweep across space like cosmic lighthouses. When these beams point toward Earth, we detect them as regular pulses of radio waves, X-rays, or gamma rays. Only about 30 magnetars have been confirmed to exist in our galaxy, making them among the rarest types of stellar objects. Their extreme magnetic fields gradually decay over time, with most magnetars remaining active for only about 10,000 years before their magnetic fields weaken sufficiently that they resemble ordinary neutron stars. TUN 618. TUN 618 stands as one of the most terrifying and incomprehensibly massive objects ever discovered in the universe, representing the extreme upper limit of what black holes can become. This hyperluminous quasar, located 10.4 billion light-years from Earth, harbors a supermassive black hole so enormous that it challenges our understanding of how such monsters could have formed and grown to such incredible proportions in the relatively young universe. The supermassive black hole at the heart of TUN 618 contains an estimated 66 billion solar masses, making it one of the most massive black holes ever measured. To grasp the scale of this cosmic leviathan, consider that it weighs roughly 16,000 times more than Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. If this monster were placed at the center of our solar system, its event horizon would extend well beyond the orbit of Neptune, encompassing our entire planetary system within its point of no return. The discovery of TUN 618 began in the 1950s during astronomical surveys designed to catalog blue stellar objects in the night sky. Initially classified as a faint blue star, its true nature remained hidden for decades, until advancing technology revealed that this seemingly ordinary point of light was actually one of the most luminous objects in the observable universe, shining with a brightness of 140 trillion suns. The immense luminosity of TUN 618 comes from the violent process of accretion, where matter spirals into the central black hole at an extraordinary rate. As gas, dust, and even entire stars fall toward the event horizon, gravitational forces compress and heat this material to temperatures exceeding millions of degrees. The resulting accretion disk glows with such intensity that it outshines the combined light of hundreds of billions of stars. creating a beacon visible across most of the observable universe. What makes TON 618 particularly unsettling is not just its current size, but the implications of its existence in the early universe. The light we observe from this quasar left its source when the universe was only 3.7 billion years old, less than 1/3 of its current age. This means that somehow, in the relatively brief cosmic time since the Big Bang, this black hole managed to accumulate a mass equivalent to 66 billion suns. The rapid growth required to reach such enormous proportions presents a significant challenge to current theories of black hole formation and evolution. Even if TON 618 began as a supermassive seed weighing thousands of solar masses, it would need to consume matter at an almost impossible rate to reach its current size so quickly. The black hole would need to feed continuously at or near the theoretical maximum rate, known as the Eddington limit, for billions of years without interruption. The environment around TON 618 must be utterly hostile to any form of life as we understand it. The intense radiation from the accretion disk would sterilize planets across thousands of light years, while the gravitational effects would disrupt the formation of stable solar systems throughout the surrounding region. Jets of high-energy particles, accelerated to nearly the speed of light, stream away from the black hole's poles, creating death rays that extend across millions of light-years of space. The existence of TON 618 forces astronomers to confront the possibility that the early universe contained mechanisms for creating and feeding black holes that no longer operate today. The event horizon. The event horizon represents the most terrifying boundary in the universe, an invisible sphere surrounding every black hole that marks the absolute point of no return. This cosmic threshold exists not as a physical surface that could be touched or observed directly, but as a mathematical boundary in spacetime itself, beyond which the fundamental nature of reality breaks down, and the normal rules of physics cease to apply in ways that human minds can comprehend. The concept of the event horizon emerged from Carl Schwarzschild's solution to Einstein's field equations, developed in 1916 while Schwarzschild served as a soldier on the Russian front during World War I. Working in trenches between battles, he calculated the geometry of spacetime around a massive, non-rotating object and discovered that at a specific distance from the center, something extraordinary happens to the fabric of space and time itself. The size of an event horizon depends entirely on the mass of the black hole it surrounds. For a black hole with the mass of our Sun, the event horizon would have a radius of approximately 3 kilometers, double the mass, and the radius doubles as well. This relationship, known as the Schwarzschild radius, means that supermassive black holes possess event horizons that can stretch across distances larger than entire planetary systems, while stellar mass black holes have horizons measured in mere kilometers. What makes the event horizon so fundamentally terrifying is the complete breakdown of causality that occurs at this boundary. In normal spacetime, cause precedes effect, and information can travel from one location to another. However, at the event horizon, the curvature of spacetime becomes so extreme that all possible paths lead inexorably inward toward the central singularity. Even light, traveling at the maximum possible speed in the universe, cannot escape once it crosses this threshold. From the perspective of an outside observer, the event horizon creates one of the most disturbing phenomena in physics: time dilation taken to its absolute extreme. As an object approaches the event horizon, time appears to slow down dramatically due to the intense gravitational field. To someone watching from a safe distance, a person falling toward a black hole would appear to slow down and freeze at the event horizon, their image becoming redder and dimmer until it fades from view entirely. However, from the perspective of the falling observer, the experience would be entirely different and far more horrifying. They would pass through the event horizon in what seems like normal time, completely unaware that they had crossed the point of no return. The gravitational field would continue to strengthen as they fell inward, stretching their body vertically and compressing it horizontally in a process that physicists have grimly nicknamed spaghettification. The event horizon also represents a fundamental limit to human knowledge and observation. No information can ever escape from beyond this boundary, meaning that whatever happens inside a black hole remains forever hidden from the outside universe. This creates what physicists call the information paradox, a conflict between general relativity and quantum mechanics regarding whether information that falls into a black hole is destroyed or somehow preserved. In 2019, the Event Horizon Telescope collaboration achieved the remarkable feat of imaging the shadow cast by the event horizon of the supermassive black hole in galaxy Messier 87, providing humanity's first direct visual evidence of this cosmic boundary.